Welcome everybody, welcome to my another lecture in data structure and algorithm analysis. So in this lecture I will mainly discuss an introduction to hash tables. Okay, so like other data structure like array, linked list, stack and queue, so a hash table is a data structure. Okay, so mainly a hash table is used for quick searching. So in order to make our searching process easier and faster, we mainly use hash tables. So let us go quickly. What do we mean by hash tables and then searching in quicker way? Okay, so let us do some recall some our background knowledge about searching algorithms. So we know that linear search algorithm, that in linear search algorithm, so data values are placed in an array. Okay, so then data values are placed in any order, right? For instance, if this is an array, so the first index is 0. Let me do it. First index is 0, then 1, 2, 3, 4, 5, 6, 7. Maybe we have 8 data elements over here. Okay, so index start from 0 to 7. Okay, so then we know that searching complexity or the time complexity for linear search algorithm is big O n, right? For instance, if we want to check whether a value like 10 exists or does not exist in this array, so what do? We start our searching from the beginning and we go one by one to all the way end. So in case we do not find it, or in the worst case we may find it all the way end. So in both cases, so our time complexity for linear search algorithm is big O n, right? So we know that there is another approach of searching that is called binary search algorithm. So in the binary search algorithm, so data values are placed in order, like in sorted order, like in, for instance, in ascending or descending order. Okay, so for instance, in this array data are already sorted, so 3, 4, 5, 6, 7 and so on. These are the indices. Okay, so data are already placed in sorted order, ascending order, and in case if we want to find whether our target value 10 exists, what does not exist. Okay, so then what do? We check for 10, we find the middle element and we check with the middle element. If it does not match with the middle element, so then we go either left side or right side based on our target value. Okay, so that in case of binary search algorithm, we know that our time complexity is reduced to log n. It's base 2, so okay, log is so LGN. Okay, so that is better, right? So and also in the linked list we know that the time complexity is big O n or theta n, for we can say theta n or whatever you say in the worst case. Okay, so now in order to reduce time complexity for searching process, so hash tables are introduced. Okay, so the goal of hash table is to develop a data structure that will give us pretty constant time. So for instance, we say that for time complexity will be big O 1. So 1 means 1 millisecond or 1 microsecond, whatever you say, that is a constant time. So that the goal of hash tables is to implement a data structure that will reduce our time complexity for searching, right? Okay, so that is the concept or use of hash tables. Okay, so in order to implement hash tables we use hash functions. So hash functions are mathematical functions, okay, and the process is called hashing. So hashing means, what do we mean by hashing? So hashing means slicing, right? Slicing. And function, that means fn, f of a, fn, we can say y equal to fx is a function, right? So we will use like this kind of function in order to develop our hash table. So there are different kinds of hash tables, and since hash tables are developed based on hash functions, so based on the variation of hash functions, and there are different types of hash tables. Okay, so now let us jump to the book and let us see what does the book have. Okay, so this is the hash table. So I know the page number will be 274. Okay, so you see that our goal to reduce the searching time for hash tables. Okay, so the simplest and one of the naive way of developing hash tables is called direct address hashing. So what is meant by direct address hashing? So if we consider a very simple hash functions, for instance, let us think that we have this value. Okay, we will consider this value. Okay, so for instance, let us draw this value quickly. Okay, so let us think that these are key values or given values, data values. So 2, 7, 9, 6, 13, 3, 11, 12, whatever we have. Okay, so these are key value, and we use a very simple hash function. For instance, k of x equal to x. For instance, f of x, y equal to fx equal to x. For instance, if our function is like this. Okay, very simple. Okay, so then let us draw another table over here. So on the right tables, we consider this as values. Okay, so these are keys and these are values. Okay, so implemented with an array. Okay, so then array index with 0 to all the way 12. Okay, so in a simple addressing, so since our hash function is very simple, that k of x equal to x, that means y equal to fx equal to x, something like this. So what we do, so since there is no change from independent variable to dependent variable, so what we do here, so 2, so according to this function, so 2 will be put here in 2 will be here put in 2, and like 7 will be put at place 7, 9 will be put at place 9, and then 6 will be put at 6, 13 will be put at 13 over here. Okay, and so then we have a place 13 over here, for instance, say, and then 3 will put over here, and then 11 will put over here 11, and then 12 will be placed over here. So then if we now, how about the searching process will be? So in order to search a value, so we will go its own position, right? So in order to search the element 2, we will go with index 2. In order to search element 7, we will go with index 7, right? Very simple. So that means the that time complexity will be definitely equal to a constant, right? We go 1. So we can quickly search an item from the array. So this is very intuitive, right? So but there, think about that, there are some limitations over here, right? So what are the limitations you do think? Okay, one of the limitation is that, for instance, if you have a large another value over here, large value, for instance, that is 100, that value 100. Okay, so another value 100. So then what do we need to do in order to use this direct or simple addressing? We need to expand our value, this array, with 100 index, right? So then in this case there will be a lot of empty cells, right? So although you see there are a few empty cells over here, but these are nominal. But in case of a large value, if we have a like outlier, any outlier values, for instance 100 or 1000, or if we have a million, a value is very large amount, right? So then we have to expand our value, this this array. Okay, so according to, in order to fit our that value, largest element, right? So then there is a scope, okay, of misuse our memory, right? So in order to save our time, we are also misusing our memory space, like there is a trade-off between time and memory, computer memory, right? So that is the process. Although this looks a good process and intuitive, but there is not an efficient way for developing our hash table, right? Okay, so okay, another problem, okay, another problem might be, okay, so for instance, what we do if we have another value, it comes like 3, with another value that comes with another value 3, and then 3 comes again, and 3 same value comes again and again. There are multiple or duplicate values, right? So then what do we need to do? So we cannot go just simply over here with index 3, right? Because this place is already used, right? So this is another limitation. So then we need to do what we can do. So definitely there are ways to resolve this issue, this kind of issue. For instance, we can create a linked list over here. So for each cell, we can, instead of using a simple cell, we can use linked list cell. So no matter how many 3 comes here, so we will add 3, 3, 3. Okay, all of the 3s over here we can add, right, one after another. Okay, so that means what do we need to do? We need to think that we need to think about other addressing way. Like that means we have to use different hash functions or different hashing process in order to make this, in order to make our hash tables efficient, so that what we can do, we can save our memory space, reduce our memory capacity, right? For instance, if we find some way that for another value, for instance another value, for we are thinking, for instance the value, next value, it comes as 100 or 1000, whatever we can get it, we can use one of the unused memory space. Okay, that will be our another way to make our tables, hash tables. Actually hash tables is more efficient, okay, and more useful. So actually hash tables is the combination of key and values. So both the combination of key and values, so we call this hash table. Okay, so in order to do that, we need to think about other hash addressing process. Okay, so let us go to the book, and the book will see that there are other addressing process in order to make our table. So let us see what do we have here in the book, then I can discuss. Okay, so what is our goal? Our goal is to use better hash functions, right? So there are some ways to develop better hash tables using different method. One of them, another method is called division method. So this division method is using modulus division method. Okay, so I'm coming here, and then there is another one is called multi application method. Okay, and let us see that there is universal hashing, and then there is quadratic hashing, quadratic hash functions. So okay, these are called open addressing. Okay, maybe we'll discuss open addressing in our another lecture. So let us go for this one. So in this lecture, let us limit our discussion with division method. Okay, so in the division method, what we do, we use just division process. So that division is the modulus division to create our better hash function. Okay, so what we do, we map a key value k into one of m slot by taking the remainder of k divided by m. So okay, so let us this is our target. Okay, so this is our target. So let us explain what do we mean by this. Okay, so our next process will be division method. Or we can say modulus method. So instead of using this simple hash function, what we will use, so we will use k of x equal to x so we say these are x. Okay, x modulus m. M any number. M is any number. Okay, so for instance 5, 10, 15, whatever you say. So for simplicity, whatever we think, for instance, let us consider n equal to 10. For instance, let us consider n equal to 10. So then if our hash function is here k of x equal to, okay, this x modulus 10. Okay, so in that case, if we use that hash function, so then whatever the value, we can say over here 1000, so 10,000, right? So we can say for this one, so 10,000 modulus 10, 10,000, what is our 10,000 modulus 10 will be 0, right? So that means instead of expanding our value array to up to index 10,000, what we can do, we can put this value, this key where in our values table at position 0. So that means here we will put 10,000 value over here. Okay, so that is another way, right? So now in case, so we have here, we see that what is my array size over here, 0 to 13, that means array is 14, right? So now if I get another value over here, for instance 23. Okay, so instead of 23, Okay, or for instance we have another value 25. Okay, so we know that 23 modulus 10 will be 3, so it will go to in position 3, right? Okay, so and then for 25, so 25 modulus 10 will be 5, so this 25 will be placed where? So okay, so 25 will be here, right? Okay, so let's come back to 23. So 23 actually it will go to the position not in index 23, so it is going to the position 3, right? So that means it will get 23 over here, not 3. Okay, so we have solved one of the issues, right? So that means instead of expanding our value tables, so what we can do, if we use division modulo the division or modulo method, so then we can use one of our unused space in the value table to put our keys, right? Okay, but so one problem is resolved, one of the issues is resolved, right? But still there are issues. Okay, so what the issues, for instance, if we have value 23, 33, 43 and something that all have same number of remainder. Okay, that is, so then we will have 3 3 3 3 over here, right? So in order to solve that, what we can do, we can use over here a linked list. So a linked list, we know that for every element node it contains a value and address of the next element, so that means the next element it will go and then it can go to the next element, right? So then we can consider that here is the main position, and then we can use another jump, or we can say this offset value, so in order to go to the next value 23 or 33 or 43 or someone, right? So that is another way, one of the ways to implement this. Or we can use a different kind of hash function, so that we can look for the next unused memory space. For instance, this is the next unused memory space, like this one, right? Or this one, these are the next unused memory space. So instead of using a linked list over here to put 3, 23, 33 and 43, if we could have a different way, for instance, we could put 3 over here, but 23 in this place, 33 in this place, and 43 in this place. So then we have another better way, right? So to use our value table and then reduce our memory misuse, right? So our next approach will be to consider a different kind of addressing technique that we can implement this way, right? Okay, so okay, so now let us see the book. Is here. Okay, so this is the division method. One thing, so in the division in the book it is used h of k, so no problem. So here don't be confused. So instead of using the function, by calling the function k of x, we can say h of k, no problem. So it's h of k. Okay, so h of k equal to k mod m, right? So h of k, whatever function you say, equal to k mod m. Okay, so I think it's not an issue whatever variable name you can say, but let me make it similar to the book. H of k equal to k mod m. Okay, so again this is h of k. So the name one was h of k equal to k. So these are k values. Okay, so these key values, each of the key values is k value. Okay, so the division method, like the third one is called multiplication. So let me get some space here. Okay, so third one is multiplication method. So what is multiplication method? So here what we are doing over here, so in the division method we are just using simple modulus division operation, right? So but in the multiplication method that instead of simple, in addition to the simple modular division, we will use another constant number to multiply our key numbers. Okay, key numbers. So let's see how. Okay, so in the multiplication method, so let us go to the book and jump to the book. So in the multiplication method, it's a two steps method. Okay, so in the multiplication method, for creating a hash table, it operates in two steps. In the first step, what we do, we multiply the key value k by a constant number within range 0 to 1. That is a constant that is less than 1 but greater than 0. It's positive constant. For instance, the number something like this, whatever you say. Okay, any number. Okay, that will be a value. Okay, and extract the fractional part of k. Okay, and then in the second phase, then we multiply this value by m. Then the second phase, whatever the we multiply the fractional part, we get the fractional part, we multiply this value by m and take the floor of the result. Okay, so that will be our position. That result we get our position in the value table. So in shortcut, the hash function is like this. So kx equal to, so then floor of, so first ka mod 1 over here. Okay, and then and then by multiply by m, and then we take the floor. Okay, so here ka mod 1 means the fractional part of ka, that is ka minus floor of ka. Okay, so if you go through the book content, if you see there are some examples, and then how do we calculate this? We use this hashing, use multiplication method for creating a hash table. Okay, but since in addition to this multiplication method, and as we discussed that the division methods, so there are some recent and universal hashing functions that are more intuitive and more better and easier to implement. Okay, So now let us discuss some of those. Okay, so those in universal hashing functions, actually there are two hash functions are used. Okay, so two hash functions are used, and then we call this actually is open hashing. Okay, so let us go. We use the actually concept of probe. Okay, and then let us see that what do we have in the book, then I will discuss this in with example. Okay, so that we use the probing concept. Okay, probe means is kind of offset. Okay, so probe means kind of offset, and then for instance where in our discussion, right? Okay, so that we discuss that we want what we want in our final implementation. What we want to use unused memory, unused spaces, right, for our value table. So then whenever we have some unused cells spaces in our value table, for instance that place was unused. So here what is the difference between its original position? It was supposed to be originally in 3, right? 23 was supposed to be in its original position 3, right? So here we thought that 23 would become here, and 33 will come here, and 43 also will be here, right? So we discussed that, right? So for both, or for 3, 23, 33 and 43, for all of these kind of numbers that have the right digit or modular 10 upper value is 3, so their original value position are expected at 3 with index 3, right? But since 3 this value was occupied, so we are looking for next empty positions, right? So 23, we got first position 23, so we put 23 over here. So the probe means over here what is the difference between its original position to here, how many steps we need to do. So for instance, first, in order to get 23, we need to first go to land to 3 and then jump to position 1 more step, right? So the 1 plus 1 is 2. Okay, then 43. Okay, then 33 it was supposed to be in position 3, but since all of this is occupied, this is occupied, this unoccupied, this unoccupied, this unoccupied, and this place was free. So then we internally step down here. So 1 to jump here in 3, then 2, 3, 4, 5, 6. So for 33 is probe is 3, and then for 23 is probe is 2. Okay, and then like 43 is probe is 1 for these 2, 3, 4, 5, 6, 7 and 8 and so on. Okay, so this value are called probe value. So that means in order to find the nearest empty position, we use another function to find that position. Okay, that is the concept of using probing. Okay, so then what we do, so in this process there are two kinds of probing. Actually one is called linear probing and another is called constant quadratic probing. Okay, so for the linear probing, what do we use? We use like for, let me write it down here. Okay, but without probing. Okay, so for the what is that called, division. Okay, for the division process, division method, what do we use? We use h of k equal to k mod m, right? Okay, But here, instead of this using k, directly k over here, so we will use another variable, so that is called h of k, and then I for index, or we say offset, or here we say probe, okay, equal to, so here there will be another function for this one. So if my this function equal to like something like h dash of k plus I, and then mod, so you can write mod like this, mod m. Okay, so that means instead of for linear probing, okay, so instead of using this k directly over here, so we can use another function. This one will be used for offset. So how many steps it goes down from its original position, okay, that is called the linear probing. So this method is a linear method, okay, this is linear probing. And there is a quadratic probing. Quadratic probing it means that for simplicity, instead of using I over here, this is linear I, right? For quadratic, so this is same thing, h of ki ai equal to, what we do, h dash of k plus something, for instance c1i plus c2i squared, okay, something like this, mod m. Okay, so that means this is a quadratic function. Or even if you c1 equal to 0, so then we can say the I squared. Okay, for instance, for simple method, for instance, in a simple method, we can say h of ki equal to, for instance, whatever we say that, say for instance 2k plus I mod n, and here we can say equal to 2k plus I squared mod n, and here I will be, the I value will be 0 to 1 to less than m minus 1, and here I value will be 0 to m minus 1. It cannot reach to m. Okay, so this is the concept of linear probing. That means our probing value we are using with a linear function, and but here in quadratic probing we are using a quadratic function. So then what are the advantages of using linear probing or quadratic probing? Okay, so let us discuss this with our same examples, that we are discussing in our lecture. Okay, so here so let me get some extra space here. Okay, so we are discussing probing, right? Okay, actually the concept of probing, it came from the concept of open addressing. Okay, so that means open addressing. Actually the previous two are close addressing. Okay, so this is open addressing. So open addressing means we can use any open method, any method, any function, open function for hash function. And in addition to hash, in order to access our free space, we that means offset values, so we use probing. Okay, so one is called linear probing. And two is called quadratic probing. Okay, so in the linear probing, what we want to do, for instance, let us see our hash function is like h of k equal to k plus I, okay, mod m, okay, and then I values I equal to 0 to m minus 1. Okay, so then what is our here for, so then we're discussing 23, right? So 23, so for 23, so then k value is 23, right? So that means for 23, so that means h of 23, right? H of 23 equal to, so 23 plus I, actually I, that means I 0 to n minus 1, here n equal to our 10, we consider n equal to 10, right? So that means I will be 0 to 9. To 9. Okay. And so this value is 9. Okay. So 23 plus, when I equal to 0, then 23 plus 0 mod 10 equal to still 3, right? So it does not work for us, right? So then we need to increase I value over here. So the next value will be, so then 23 plus 1, okay, mod 10, then 24 mod 10 equal to 4, right? So that means we go to the fourth position and we find an empty space over here, right? So that we put 23 at position 4, right? So that means prob here, prob value will be 1 for landing at 3, and then the second value will be second step will go into, we need one more step to go into the 4, right? So the prob will be 1 plus 1, that means 1 plus 1 equal to, you can say 2, or if we do not consider this the first landing, then we can say 1. Okay, and then for h of 33, right? 33 will be, so 33 plus 0 does not work, right? Modulus 10, so the 0 does not work, since the 0 is will be position here. So if we say 0 I equal to 0, then 33 plus 0 mod 10 equal to 3, so it will not work. So then 1 for I value, so I value 0 will be next, will 1 will be fourth value, that is also occupied, so 4 will not work. So then I value will be 2, so then 2 means for 35, that means 5, that is already occupied, so 3 will not work. 2 will not work also, so how about 3? So then 33 plus 3 is then 36 mod 10 equal to 6, and that is also occupied, and so that will not work. So then how about the next one? The next one will go 4, right? You see the next value, I value will be 4, right? So then 37, this is also occupied, so it will not work. So then what value it works? So we see that it works for value 5, right? I value 5, right? So if we say I equal to 5, I value equal to 5, then we say 38 mod 10, that means 8, right? So in 8 position we put 33, right? So we got 33. Okay, and similarly for age of 43 we will get the prob value, so that means 8, right? And then prob will be, so what is prob over here? Prob will be, so here 1 2 3 4 5 and 6, so prob will be 6. Okay, so let me delete this one. Okay, so now say for age of 43. Okay, 43 equal to 43 plus I mod 10, right? Okay, so what I value will be good for this 43. Actually we see that for I, 0 does not work, 1 does not work, 2 does not work, 3 does not work, 4 does not work, 5 does not work, 6 does not work. Okay, and then okay, okay, one more thing, maybe I did a mistake at the beginning. So I could say over here, since our this table, actually this should be better if we have 0 to m minus 1. So if we consider m over here as 14, that would be nice. Okay, for instance, for now we can say, for instance, if we consider m equal to 10, then we should have this value table with size 10. Okay, but you can do that. Okay, so now we see that there is a way that we can use, by using probing, we can use this unused space to fit our key value in next unused space, right? So now the next one we are discussing, the one is a quadratic probing, right? So quadratic probing, what we will do, so then for instance we say k of h of k equal to k plus I squared, for instance we say, and then mod whatever, say 10 or 14, whatever you say over here. So 10 or 14, whatever you say over here. So in that case, what will happen, then you will jump from one place, and there is a scope that you will get another value available over here. But in this way, so you can check for all of the key values for its appropriate values in the appropriate position in the value tables. But one more thing is that by using even linear or quadratic probing methods, there may be case, it may happen that for some key values you may not get any available position. That means for some key value it may happen that it is the, since we are using modulus operation, right, the modulus value can be same thing, same values, can be iteratively same values that can always that may always direct to an occupied position. In that case it does not work. In that case we may not find an appropriate position in the value table. Okay, that means we cannot, in that case we cannot put the key value in the value tables, keys in the value tables. Okay, so that what we have, what processes we use, even simple or direct addressing or open addressing, or so this is called close addressing, first one. So whatever we use, close addressing or open addressing, what do we use, no matter. But we will see that our searching process becomes, for instance, if we can land any position that is constant time, the first landing is constant, right? So that Tn, whatever we are going, first is constant, some constant plus we have another offset value. In the worst case, we may have some offset value, right? So that offset value is also constant, right? So that plus another constant. So that means our ultimate total searching value will be constant. Constant plus constant is constant. So we denote constant and constant by big O1, right? So that in case of hash tables, so we get constant or pretty constant searching time. Okay, but as I mentioned, that there is a trade-off between memory space and time, saving time and using memory space. But in order to make an adjustment or develop efficient hash tables, we use different kind of hash functions and hashing process. Okay, so I like you, so now read through the book chapter, and then we will understand this. Okay, so okay, there's another hashing is called perfect hashing. Maybe I may get another lecture to discuss this. Okay, so now in a days, if you do a research and if you do Google search, there are many hash functions, and people are doing research on hashing and developing better hashing hash functions and hashing algorithm. Okay, but the concept is pretty same, and these are the foundation of hashing. Okay, thank you so much, and I will see you in our next lecture. Bye bye.